Hello everyone. Let us continue our chapter Solutions and Qualitative Properties. So today's topic is Raoult's law. According to Raoult's law, the partial vapor pressure in a solution is equal to the vapor pressure of pure component multiplied by mole fraction of that component in the solution. Let us consider a binary solution containing two volatile liquids A and B. As both A and B are volatile, so there would be both particles of A and B in the vapor phase. So in this diagram we can see that A and B both are volatile liquids, so vapor phase constitute of the particles of both A and B. Therefore, according to Raoult's law, PA is equal to XA into P naught A and PB is equal to XB into P naught B. Here, PA is partial pressure of A, P naught A is vapor pressure of pure component A, XA is mole fraction of A, and PB is partial pressure of B, P naught B is vapor pressure of pure component B, and XB is mole fraction of B. Since both the components A and B are volatile, therefore the total vapor pressure of P is given by P is equal to PA plus PB, and putting the values of PA and PB in this equation, we get P is equal to XA P naught A plus XB P naught B. Consider a solution containing non-volatile solute B in solvent A in a container, because only A is volatile. Therefore, there would be the particles of A in the vapor phase only. Now, the Raoult's law, P is equal to PA is equal to XA P naught A. Here, PA is the partial pressure of A, P naught A is the partial pressure of pure component A, XA is mole fraction of A, and P is the vapor pressure of the solution. Since here only one component is volatile, therefore the vapor phase will constitute of only one component. We can also write this equation as vapor pressure of solution is equal to the mole fraction of solvent into the vapor pressure of pure solvent. In other terms, Raoult's law can be expressed as the vapor pressure of liquid in a solution is directly proportional to the mole fraction of that liquid in the solution. That is, P is directly proportional to the mole fraction of solute. So here we can see there are two containers. One is containing pure water and other is containing sugar solution. So the container containing pure water is having the particles of water in the vapor phase, and also the container containing the sugar solution is also having the particles of water in the vapor phase. But here in case of the pure water, there are more particles in the vapor phase, and in case of sugar solution there are less number of particles in the vapor phase. This means that the vapor pressure of pure solvent is always greater than that of the solution, because here the surface area covered by the water molecule is more as compared to that in case of the sugar solution. Now, ideal and non-ideal solutions. Ideal solutions are those solutions which obey Raoult's law over the entire range of concentration. For them, PA is equal to XA P naught A and PB is equal to XB P naught B. While the non-ideal solutions are those solutions which does not obey Raoult's law over the entire range of concentration, and PA is not equal to XA P naught A and PB is also not equal to XB P naught B. Here, in case of ideal solution, the enthalpy change on mixing and volume change on mixing is 0. This is because the intermolecular attractive force between the solute molecules and solvent molecules are nearly equal to those present in the solute and solvent molecules. That is, AA and BB interactions are nearly equal to those of the AB interaction. Here we can see that this is solvent molecule and this is solute molecules, and solvent is A, solute is B, and there is force of attraction between solvent molecules and also in case of the solute molecules. But when we mix them, the magnitude of the intermolecular force in A and B is nearly same as that was in case of the pure solute and pure solvent. Therefore, there is no change in the enthalpy of mixing or volume of mixing, right? But this is not the case in the non-ideal solution. Here the intermolecular attractive force between the solute and solvent molecules is always greater or lower than that was present in case of pure AA and BB interaction. So this is the graph for ideal solution, and when the mole fraction of A was 1, then the mole fraction of B was 0, and then the vapor pressure was P naught A. So here it is obeying Raoult's law, and gradually when the XB was 1 and XA was 0, then the vapor pressure was P naught B, and total vapor pressure is PA plus PB. Now the types of non-ideal solution, there are two types of non-ideal solution. One is the non-ideal solution showing positive deviation from Raoult's law, and other is the non-ideal solution showing negative deviation from Raoult's law. So first is the positive deviation from the Raoult's law. Here the A-B attractions are weaker than the average attraction of the pure component of the mixture. Therefore, the deviation will be positive as the partial pressure of each component and the total resultant pressure are greater than that of the pressure expected from the Raoult's law. So here we can see that here are the two components A and B, and there is weak A-B interaction in case of the positive deviation, and as a result of weak intermolecular forces, the molecule they tend to escape in vapor phase easily, and hence the partial pressure of each component is more than we were expecting from the Raoult's law. Therefore, it is showing the positive deviation from the Raoult's. So here we can see there is increase in the partial pressure of both the components A and B, and hence the total vapor pressure of solution is also showing an increase. And in case of negative deviation, there is A-B attraction is much stronger than the average of the attraction in the pure component of mixture, and hence the partial pressure of each component and total resultant vapor pressure is less than the expected on the basis of the Raoult's law. So here we can see that there is strong AB interaction, and hence when there is strong AB interaction, the molecule have less tendency to escape as the vapors. Hence there are less molecules in the vapor phase, resulting in the less vapor pressure. Therefore it shows negative deviation from the Raoult's law. Here we can see that both the components they are showing negative deviations, and hence the total pressure of the solution, total vapor pressure of the solution is also decreasing. So when we compare both positive and negative deviation, so in case of positive deviation, the AB interaction is less than AA and BB interaction, while in case of negative deviation, AB interaction is more than AA and BB interaction. And delta V on mixing is positive, delta H on mixing is also positive, and here both are negative. So the process of dilution is endothermic and process of dilution is exothermic. So here are some examples of positive deviation: ethanol, cyclohexane, carbon tetrachloride, benzene, benzene acetone, carbon tetrachloride and chlorine. And the examples of negative deviation are chloroform, benzene, water, hydrochloric acid, water, nitric acid and acetic acid and pyridine.